Hello, dear audience. Thank you so much for being with me in another artificial neural networks tutorial video. We talked about neural networks and activity functions. We said that after doing the matrix multiplication, we should apply a nonlinear activity function and finally calculate the output. In the previous video, we reviewed two of the three famous activity functions. We examined the benefits and activity of a tangent hyperbolic function and the sigmoid function. In this video, we want to check how the third common activity function, which is the ReLU activity function, can solve these disadvantages. We have said that the disadvantages of the sigmoid function are the saturated areas, the non-zero average of the outputs, and the existence of the expensive exponentiation operation, among which the second problem, which was the non-zero average, non-zero mean, can be solved if the tangent hyperbolic function is replaced. But two other problems still remain. There is no exponentiation in the ReLU function, and the calculation part is done much faster. In the positive regions, we always have a constant positive slope and it never saturates. But in this function, the slope is 0 in the negative region. For example, at x is equal to negative 10, the gradient becomes 0 and we do not learn. In addition, in this function, we are also facing the problem of non-zero averages. This function is not differentiable at the point which is x is equal to 0, because the right limit and the left limit are not equal. Of course, this is not a very big and serious problem because it rarely happens that the input of this function is exactly 0. And if it happens, you can use the left and the right subgradients. But the problem of the function is significant in the negative region, although it performs very well in positive areas. Neurons that are never updated and activated are dead neurons. About 20% of neurons are dead. They have no benefit, but they exist in calculations. To solve this problem, instead of defining the bias with value of 0 in the ReLU function, let's define this bias with a very small value and close to 0. It is not clear whether the solution is definitely the answer to this problem or not. A better solution is to consider a very low slope for the function in the negative part. That is, we maximize between x and, for example, we can consider a factor. For example, 0.01, we can multiply 0.01 into the x and have a maximum between x and this product, this multiplication product. We call the resulting function leaky ReLU. This function exists to solve the set problem. There is a generalization of the leaky ReLU function, which is the amount of this coefficient, which is considered here 0.01. This is learned as a parameter in the problem to this generalization of this function, which is called parametric leaky ReLU or P leaky ReLU. There is another function that is actually generalization of all of these three types of functions from the ReLU family. We call this function max out. The slope of each line is a parameter in this function that must be learned. For example, here between these two lines, we should take the maximum. This function has the same advantages as ReLU and a leaky ReLU. For example, this function has a linear behavior. The problem with this function is that the number of parameters increases. In practice, it is recommended to use ReLU by default. Testing each of these functions is a time-consuming activity. Which of these function to use depends on the problem itself. For example, in the picture, in the image processing, it is better to use ReLU and the family of this activity function. But for example, tangent hyperbolic may be better in a text processing problem. Before applying the activity function, it is necessary to pre-process the data. For example, it is necessary to transfer the data in such a way that their average becomes 0. By removing the average, the common information between the data is removed and the focus is placed on the differences on which the classification is done. For this, we average the columns. In order to apply the averaging on the columns, we use axis is equal to 0. This should be done on the columns because the columns represent the features and the rows are the data itself. Another thing that we have to do in most cases is to equalize the range of features. For this, we must equalize the variance or deviation from the standard deviation actually. In this way, the dispersion of the data is almost equal. We call this normalization. This task should be done in problems where the dispersion of data is very difficult in different directions. But in image processing, where this dispersion is not very different for different data, it is not necessary. Other tasks are done in the pre-processing stage. In cases where our features are correlated, we must remove the correlation so that the data is independent and eliminates a redundancy. We can use a PCA for this. When after removing the correlation, we try to make the dispersions in every direction small and equal, this process is called whitening. Two things can be done to zero the center, zero the mean. Suppose you have, say, for example, 50,000 data in the training set in the CIFAR problem. The dimensions of each data are 3 multiplied in 32 multiplied in 32. Averages means can be obtained in each column, each feature, and thus we have a vector. Now you can subtract this row from each row of the set matrix with one command. You can also average all the pixels, both for red, blue, and green channels, and then subtract this average from the image. This method is more common. It is also used in AlexNet. An important point is the initialization of the weights. The reason why it was not possible to use deep neural networks for many years was that we did not have the possibility to initialize the weights optimally. If at first we consider the value of all these weights to be 0, all neurons in all layers work the same and do not learn any different features well. The neurons of each layer work exactly the same. That means we cannot learn different features. We have to somehow break this asymmetry. For this purpose, for years, we have randomly set the weights with very small numbers close to zero. We considered a Gaussian distribution and generated random numbers around the 0 point. To do this in Python, we must use the random module. Until now, this method has been common. Because actually until now, I mean until up to some years ago. Because the number of hidden layers of neural networks was small, but if we increase the number of layers, we can produce higher level features and solve more complex problems. This lack of success in producing high level features has been happening since the 80s, the centuries, the years of 80s. But they have recently realized that the solution is to change the method of initialization of weights. Here I have shown this problem in action, in practice actually. I have implemented a neural network with 10 layers. We have 500 neurons in each layer, and currently the activity function used in all layers in tangent hyperbolic function. Finally, we try to check the output of different layers. For this, we calculated the mean and standard deviation and draw histograms. I have put the relevant codes in the files for you. Be sure to pay attention to them. You can see that with more layers the gradient disappears, and this means that we will not learn. So this method is not suitable. You might say that now that small w's are causing this problem, let's initialize the w's with large values. In this case, you can see that according to the fact that we have used the hyperbolic tangent hyperbolic function, the outputs are either +1 or -1. So considering that we are using the hyperbolic tangent hyperbolic function, we know that the gradients are getting smaller and smaller at these points, and again this value is not suitable. That is, the neurons are saturated. So the right solution is to use Xavier's weighting method. The idea is that we generate numbers with a normal distribution and divide the numbers by the fan-in root. In this way, we have a normal distribution in almost all layers. This formula is true provided that the tangent hyperbolic activity function. But if you have used the ReLU activity function, we must add a division by 2 to the denominator of this fraction. Another point that should be used in addition to the previous techniques is batch normalization. Normalization can be done for the output of each layer in addition to the input. This task can solve the problem of gradient loss in the backward step in the backpropagation algorithm. In fact, it is effective in a better backward propagation of gradients, but there is a problem. There is a difference between normalizing input and output layers. Input normalization is much easier because we have all the inputs and we use them in normalization. But due to the fact that we use the mini-batch algorithm in practice and have parallelism, all the data are not available. That is, we only have the output of a group of data. That is, in each layer, we can only calculate the average and standard deviation for part of the data. For this reason, we do mini-batch normalization. That is, we also perform normalization for part of the data. But finally, we estimate a general average, a general mean, and a standard deviation. A general standard deviation. We will gradually update these parameters, and finally we will be close to their real values. Fortunately, the function used in batch normalization is also differentiable. Note that with whatever we do in the forward phase, we must be able to get a differential from it in the backward phase. We perform this normalization in all layers before applying the activity function, but this task causes that this work causes that, for example, where we have used the tangent hyperbolic function as the activity function in all layers, the output of the neurons is all in such a way that the averages are 0 and the standard deviation is 1. That is, the data are close to 0. In this interval where the data is located, the tangent hyperbolic function is almost linear. Our main intention is to apply nonlinear function in order to achieve more power, to solve more complex problems, and now we have lost this power. Do we really need to do this mini-batch normalization? It depends on the problem. To solve this problem, we allow this center and standard deviation, this mean, this average, and standard deviation to change. For this purpose, we add two parameters which are learned by the network, like the weights in the backpropagation algorithm. These two parameters are gamma for dispersion and beta for mean center. Pay attention that the initialization of these two parameters is not random, and the gamma is initialized with 1 and the beta is initialized with 0. To make the function smooth in normalization, we also consider an option. In difficult problems, this technique helps us a lot in improving the backward propagation of the gradients and setting weights and better finding the alpha parameter. And in fact, it can also act as a regularization. In the next video, we will solve a real problem together so that you can understand the work steps of a data scientist. Have a nice time.